Good afternoon, everyone, although it's getting so dark here in Toronto that it feels like evening, but it's not quite yet. What I'd like to do is to return to this charger for these Motorola radios. I'll take the radios out because we're not going to be looking at the radios. I'm still interested in this charger. If you've seen my earlier video on this, I'd recommend you have a look at it. I'll put a link in the description below. The problem with this charger is that I have the wrong power supply for it. This power supply is correct, it's 9 volts, but this is an unregulated linear power supply. So what that means is that when there's no load on it, this voltage drifts up to 16 volts or so. The problem with that is with the voltage drifting up, it's delivering almost over 100 milliamps to the little batteries in here, even once they're fully charged. Because of course the amount of current that's delivered to these batteries is related to the voltage that's supplied to them. The power supply in here has a couple of resistors. Well, has a series of resistors to light the LEDs and to limit the current a bit, and a diode which drops the voltage slightly. That's it. That's all that's in the power supply. And as I said, if you go look at my earlier video, you could see that. Now the solution, of course, would be to find a 9-volt power supply that's fully regulated. But just as a fun project, what I wanted to do here is think about how we could make this power supply work in this charger. So then we want to think a little bit about how we might go about that. Now one solution might be to use a buck converter power supply. This one can be current limited with one pot and voltage limited with the other, and you can set them both up. These are all, I have a number of these. These are all based on the same chip. This one has a display that shows the voltage. This one I think only does voltage limitation. I don't think this one allows you to limit current. So you could somehow cram something like that inside this case. This one I could probably fit in there. There's a lot of space in there. But that seems like overkill, and the better solution would be to replace this. The other option would be to use something like one of these. I will hold this up so you can see what it is. This is a Chinese clone regulator. Right, I'll just see if I can show you the number on that in just a moment. I've got this little Fresnel lens. I don't know if this is visible on there at all, but they are LM317. These are T's, which I think just refers to the packaging. So you could obviously get a 9-volt regulator, but this is the 317. Requires a little bit of additional circuitry. This is just a little perf board circuit I built for using one of these. I think this was to limit the voltage going to a supercapacitor so that I wouldn't blow them up. Another option would be to load down this power supply. If you loaded down this power supply, you might get it into the 9-volt range. And I do have, these are 120, and these are 100 ohm, these are half-watt resistors. So you could put a couple of those on and see what happens. That, I think, is, so what we're talking about here is within a couple of different levels of complexity, solutions to the problem of trying to control the voltage here to something that's a little bit more reasonable. Well, unfortunately, I tossed out my schematic, which I made the last time that I opened this up. Right, this uses irritating screws. So let's have a look inside this. And I'm guessing this one. Oh, first time. I think I got it first time last time too. I think I figured out what I want to do to try and get this to work with the power supply I've got. What I'm essentially going to do is replace this diode here with an LM317 regulator, and it's supporting resistors, of which there'll be a third one, a 1.5K. This is a 220 and a 20. Those, well, we'll see in a second how that's going to work out. And then this will probably go on the back here somewhere, and we'll figure out how the whole thing's going to wire together once I get it. Let me just explain the circuit. I'll draw it out, and then we'll see how it goes. So we're going to come in here from the positive. I may put a capacitor in here to ground. I'm not sure. That would just involve populating one of these capacitor spots, would effectively do that. Then we're going to go into the LM317, and this is the input. The output is going to come out this side. If I remember correctly, and I'll double check, the output is the center pin, the input is the right pin, and the adjust, which is the left pin. So this is out. And what we're trying to get out of here is 9 volts. And this capacitor I will probably put in here. This will have to be mounted somewhere at the bottom. So the interesting thing is the adjust. So adjust here will come down, and what it essentially does is there's a resistor in here which I want to be 240 ohms, but I don't have one, so we'll use a 220 and a 20. So together those are 240 ohms, and that's equal to R1. I'll see why in a minute. Then this comes down and connects in here. And then we get the other half of the divider here. This is R2, and that we're going to make 1.5K. And that will then go to ground. So it's this divider that sets the regulation point for this. And the equation that determines that is V out is equal to 1.25, which I believe is the internal voltage reference in the chip, 1 plus, let me just make sure I've got this right, R2 over R1. And if you work this all out with, R1 being 240 and R2 being 1500, you get around about 9 volts, if I've done the arithmetic correctly. So maybe I'll zoom in on that a little bit. It won't make it much better. So that's what I'm going to do. Now, what you normally do for this is you would put a pot for R2, right? For R1, it's low value. It's easier to use a resistor. But for R2, you'd usually use a pot, which I could do. But let me just going to try this first, just because I don't know where I'm going to put. I have a bunch of these sorts of pots, which would be in the right range. Sorry, I bashed into the camera. But I'm going to try the resistors and see if the math works. So I'll try to solder this together. I'm not going to try to do that on camera. And then, well, we'll see what we got at the end, whether it works or not. I don't know why I'm pulling the calculator over. We don't really need that anymore, but we hope anyway. Or the solder. So here's the circuit. So this is so let me just show you what parts are what. I'll point with the screwdriver. So LM317, that's here. It's upside down because the heatsink section here is the output, right? So that and the center pin are the same thing, which can make these very difficult to solder if they're connected to a heatsink already. So, and actually there's enough mass in that they're difficult to solder anyway. This is R1, which is 240 ohms. The two resistors are tied together at the end and covered in a little piece of heat shrink so that they don't short against what's the negative over here. This is R1 here. So we need the second part. There's the pin, the adjust pin there. So we need the 1500 or the 1.5K resistors underneath this heat shrink here, and that runs over there to the ground here, which goes right to, ties right to the plug here. Here's the input coming straight down this trace from, you can see, well, that's supposed to be a red mark, hard to see on the green solder mask. That comes through this little wire over to here, and the output is tied directly here where the output of the diode was. So input and output are there. Well, output is there, input is effectively there with this little red wire. So I have tried this, and at a very quick glance it's working. So let's see how we're doing. So there it is, it's plugged in. We'll put this back on DC volts, and I banged. No, I got them the wrong way around. But I got 9 volts. What happens when we try to trigger the charging circuit by putting some resistors across to represent the battery? Now you may or may not be able to see that, but that LED is lighting. Now, two questions about this. First, will it fit in the case? That's a big question. And the second question is, I could put a capacitor on the input supply quite easily by putting one across here, right? Because that's across. That's across the output. So I think that's what I'm going to do. I'm going to go find myself a small capacitor. Here I've got too many wires running behind it to mess around. So I'll use that position there. I'll go find, I don't know, an appropriate capacitor. And we'll try that. I don't think I'll sacrifice a good Nishikon for this. This is a cheapie, but 16 volts, more than adequate. 320 micro. And let's see, we'll just have to clean this up. Where did I put the solder braid? Here it is. I just have to clean up these pads here, just to remind myself that I am looking at the right spot. There we go, there's one. There's two. So positive on that side, negative on that side. They mark the stripe, very convenient. So that'll give us a capacitor on the output. And with this, this is converted from an unregulated power supply to a regulated one. I don't know if I'll end up putting all that video in, but I did try putting the this power supply on the oscilloscope here, and it's lovely and clean. It's just very nice, just the voltage is too high. So I don't think there's any need for a capacitor on the input as on the signs here, or on the schematic, which of course I've copied from the data sheet. Okay, so there we go. Let's check the voltage again, make sure that's still good. 8 volts, 9 volts. So I dropped the leads on the floor, and let me find these, which I'll just use to see. Yeah. Lights. So the real question will be, will this get warm? And I really doubt it. It's not going to get warm unless there's significant current being pulled through it. And as current's pulled through it, because it is a linear power supply, the voltage is going to drop, which will mean it won't work as hard. So I think we have a good solution here to the problem of an unregulated supply. It would be interesting to put a 9-volt supply on it and see how much drop there is across the regulator. Probably too much, but maybe not. I think it's rated from 1.25 volts on up, so might work. But so I'm going to see if I can get this all to fit inside the case. And that will be so that side fits, obviously. I did hold this up to see if it might fit before. And oh, look at that. It fits. So what I've done here, of course, as I said before, is build a regulated power supply out of the unregulated one by the simple addition of a regulator, thereby converting that power supply, well, moving the regulation from the power brick into the charger. Okay, so once again, we'll make sure that both of these are connected. Yeah, 8.94 volts, 8.96 volts, 8.96 volts. Let's hold these resistors over it again to see if the LED lights. It does. This one, LED lights too. I could try putting a radio in it. Just a moment. So here we have 2 radios into charge. The lights are lit. Let's have a look at, I'll grab this, at the current through I'll just unplug that for a moment. Let's have a look at what current is being drawn through the power supply. do this the same way we did in the earlier video. Put this on 2 amps. DC, we'll zero it and plug it in. So we got 183 milliamps. So what I'm going to do is let this run and see what happens. So I made one final modification to this, and that is that I pulled out the 20 ohm resistor I had in here, and I replaced it with a 39 ohm resistor to give 259 ohms on the R1 side, and that produces an output voltage of 8.5 volts, more or less. And that's because when I figured it out before, I didn't take into account the diode drop of about half a volt that had occurred with the 1N4 or whatever, we'll call it 004 diode that was in there. I can't remember which one it was. So I've dropped it down to 8.5 volts in consequence, and I did that by changing that resistor. And that gives me a charging current for both of them of, round about 127 milliamps. And so with one, you get 65 or 61. And of course, some current is being taken in the LEDs and whatnot. So let's call it 60. Now that should bring us down to a safe long-term charging current for these. I still wouldn't leave them on the charger all the time. In fact, what I'm going to do is unplug the charger when I'm not using it. But that should be a safe overnight charging current, and if you happen to leave them on for a little longer, no harm would come. Whereas the earlier charging current was double that, and that really isn't a safe charging current for nickel metal hydride batteries. I was looking at this thread, which in some of the advice here is that a maintenance charge of C40 can be done with 21 milliamps. Well, that's not working, but an overnight C12 trickle charge can be done with a constant current of 71 milliamps. This is looking at 850 milliamp hour batteries, which are, I think, what these are. That's 71 milliamps, and we're a good, probably 10 amps below that. And it says, modern cells have an oxygen recycling catalyst which prevents damage to the battery on overcharge, but this recycling cannot keep up if the charge rate is over C10. So C10 is essentially you divide the charge rate by the milliamp hour of the battery. So I think these are now at a safe charge rate as far as I'm concerned. So I'm happy with that as a solution. I think that does sound like what the charger is designed to do. Now, again, I will not keep these on the charger unnecessarily. They'll stay on the charger, but I'll unplug it when they're not being used for a long period of time. I will note that I have left them plugged in for a while, and there's no evidence of any significant heating from the regulator. So I think this is a good fix of the problem of converting my unregulated linear power supply into a regulated one for the purpose of charging these little two-way radios. Thanks for watching.